Let's have a chat today about the multiplication of radicals. Now I'm going to assume that you've seen a previous video on entire and mixed radicals and how to put a radical into simplest form, because that'll be part of this lesson. If you haven't seen it, might be a good idea to check it out, preferably before, but even after, just to make sure that you're okay with radicals in simplest form. Objectives here: to multiply monomials, single terms, monomials. 2, to multiply monomials by a binomial or a trinomial. And 3rd, to multiply binomials. So how do we multiply these radicals? Well, let's start by looking at multiplying monomials. 2 single terms, how do we do it? Since the square root of 9 times the square root of 9 is the same as 3 times 3, because the square root of 9 is 3, 3 times 3 is 9. Can we make sense out of the fact then, therefore, that the square root of 9 multiplied by the square root of 9 must be equal to 9? What if we multiply the radicands, that's the number underneath the radical sign, and have that as the new radicand underneath the radical sign? Square root of 9 times the square root of 9 equals the square root of 81. Okay, 9 times 9 is 81. Well, this seems to make sense. Seems to work because the square root of 81 is 9. And on the previous slide, we had determined that the square root of 9 times the square root of 9 is just 9. Let's look at 3 questions here. If you want, you can pause. Just write down these questions and check the answers to see what you get. We'll look at the answers on the next slide. Times 25 is 625. So root 25 times root 25 is the same as root 625, which is the same as 25. Root 2 times root 3 would be equal to root 6. Multiply the radicands. And root m times root m would be the square root of m times n. So to summarize here, multiplication property of square roots. Square root of a times the square root of b is equal to the square root of a times b. We multiply the radicands together. A good thing to remember here, when multiplying 2 identical radicals, the result will always be just the radicand. In other words, root m times root m, same as m. Root 12.6 times root 12.6 is equal to 12.6. And there's one more example there, but I think you get the picture. Well, what if we've got a number in front of the radical? What do we do then? How should we multiply 5 root 2 times 4 root 7? The factor or number that sits outside the radical to the left is called a coefficient. In the example above, we have 2 coefficients. We have a 5 and a 4. The way we multiply these would be multiplying the coefficients together and then multiplying the radicals together. It's a similar way that we would multiply terms, polynomial terms. So what would our final answer be here? We take the 5 and the 4, the coefficients, multiply them together to get 20. That's our new coefficient in the final answer. Then take root 2 times root 7 to give us root 14. The final answer would be 20 root 14. Just a little note here. If the coefficient is 1, it's typically not written, but it's implied that there's a 1 there. So if we have the square root of 5, it's the same thing as 1 square root of 5, or 1 root 5. Same thing. We just normally don't write the 1, but just be aware that it's there. So multiplying a monomial by a binomial or trinomial. So let's recall some algebra. If we had the expression 3x bracket 2x minus 8, which means we're multiplying here. To simplify, we would multiply using the distributive property, which means to multiply the monomial of 3x by each of the 2 terms in the brackets. So we got 2 terms, 2x and negative 8 in the brackets. So our result would be 6x squared minus 24x. Let's take that line of thinking into working with radicals and multiplication of radicals because it follows the same thinking. So what do you think the result would be given this expression? So in essence, what I've done is I've taken these x's and replaced them with root 5 right here. I kept the coefficients the same. So what would the result be here? So once again, we would use the distributive property. Take the single term, the 3 root 5, multiply it by the first term in the brackets, 2 root 5. Because there was a subtraction sign in the brackets, we put a subtraction sign there. And then 3 root 5 times the second term, or 8. So now we're multiplying monomials together twice. So multiply coefficients to get 6. Root 5 times root 5 is the square root of 25. Now remember, it's the same as just the radicand. That's the same as 5. So I could have written just 5 there, but I wanted just to make sure that that's how we follow the multiplication properties to multiply the radicands together. 3 root 5 times 8. So we're multiplying a radical term by an integer. We would multiply the coefficient by the integer. 3 times 8 is 24. We have 24 root 5. Square root of 25 is 5, and then take that. 5 times 6 is 30. So our final answer would be 30 minus 24 root 5. So using the distributive property as we would in algebra. So given this expression, a single term multiplied by a trinomial are 3 terms now in brackets, but the process will still be the same. I put different letters this time, x, y, and w into the expression. And our result would be 6xy plus 8xw plus 10x. I've put in 3 different radicals here, root 2, root 6, root 3 for x, y, and w. But our process is the same. Multiply the single term 2 root 2 by each of the 3 terms in the brackets. So single term out front, 1, 2, 3 terms in the brackets. So the 2 root 2 is multiplied by the first term, 3 root 6, added to the first term multiplied by the second term, 4 root 3, added to the first term multiplied by the last term of 5. So we have a situation of 3 times multiplying monomial radical expressions together. So we get 6 root 12 plus 8 root 6 plus 10 root 2. Our answer would be complete at this point and in simplest form if none of the radicands had common factors to the radicand of a perfect square. But one of these terms can be simplified. Which term do you think? If you said the square root of 12, great. 12 has a perfect squared factor of 4. So using the multiplication property, square root of 12 can be rewritten as the square root of 4 times the square root of 3. And this is important because the square root of 4 has an integer equivalent. Square root of 4 is 2. We would then take the 2 and multiply by any other coefficient. In this case, there's a 6. So 6 times 2 is 12. So we get 12 root 3. And the last two terms stay the same because their radicand 6 and 2 have no factors that are radicands of perfect squares. So our final answer is written at the bottom there. Let's move on to binomials now, 2 terms by 2 terms. So our process will be a little bit different. So let's multiply 7 root 2 plus root 3 times negative 4 root 5 minus 6. You could do something called FOIL, first, outer, inner, last. I like the box method. It's a visual representation of this. It's like we had a rectangular field. We split it into 4 parts. And we find the area of each of the parts and then add them together. Now, I recognize that when we have negative terms here, that doesn't really make sense for our distances and finding areas. But let's move a little bit beyond that, just to step back a little bit, to think about finding parts, these 4 parts, and then we have to add them together. And I just like to think of these as lengths, that this is the length 7 root 2. Now there's the plus sign, and this would be the length of root 3. And down here, negative root 5. And from here to here would be negative 6. I put the sign here. We could have put it right in front, which might have been a bit better to more clearly see what this term is. So yes, these are negative numbers, but let's move past that. We know that we have to multiply these two together. So we'll multiply these two together, which gets us the area of this portion. So multiply, now we're multiplying individual monomial radical terms. So multiply coefficients, negative 4 times 7 and root 5 times root 2. Over here, there's that invisible 1. 1 times negative 4 is negative 4. Root 5 times root 3 is root 15. And then we'd go negative 6 times 7 root 2 to get the bottom left-hand corner of negative 42 root 2. And the bottom right-hand corner would be negative 6 root 3. So the final answer is the sum of the 4 boxes. We would have to add them. So again, having to know something about adding radicals. In a previous lesson, we talked about that. Remember, to add radicals, they need to be like. That means that the radicands have to be the same. So we're looking at 15, 3, 2, 10. They're not the same, and we can't simplify them to get them to be the same. Therefore, there's our final answer. Another example, 2 root 6 minus root 3 multiplied by root 6 plus 5 root 3. Set up the box again, break it into 2 parts, a 2 root 6 and a minus 3 to represent these line segments here. And then a root 6 to here and a positive 5 root 3 to here. So root 6 times 2 root 6 would be 2 root 36 minus root 18, 10 root 18, and negative 5 root 9. Square root of 36 is 6. 6 times 2 is 12. That's where the 12 comes from. Square root of 9 is 3. So anytime we have a perfect square, we would replace it with its natural number equivalent. So negative 5 times 3 is negative 15. So we've got 3 terms here. But now the 2 integers, the 12 and the minus 15, they can be combined into 1. That's how we get this negative 3 over here. Then we can take 9 root 18 and simplify it as to 9 times root 9 times root 2. Because root 9 times root 2 is root 18. Square root of 9 is 3. And 3 times 9 is 27. So we have a final answer of 27 root 2 minus 3. Just a reminder, if you can remember, you could have put down root 6 times root 6 is just 6. It's multiplying any two identical radicals. So this could have gone just directly to 6 if you wanted. As could root 3 times root 3 is the same as 3. Another example, the dimensions of a square can be represented by the radical expression 7 root 6 plus 4. So let's write a radical expression to represent the area of the square. The square has all sides of the same length. So we're looking at 7 root 6 plus 4 squared, multiplied by itself. So if you see a binomial squared, it means that there are two binomials, 7 root 6 plus 4 and 7 root 6 plus 4. Let's set up the box method again, 7 root 6 plus 4, 7 root 6 plus 4. Let's go through and multiply every combination of our radicals together to get these 4 parts of the box. It's like finding the area of a field and then adding up the individual parts to get the final result. The square root of 36 is 6, and 6 times 9 is 294. Four times 4 is 16, so those two integers can be combined into one. They're like terms. And here we have 28 root 6 plus 28 root 6, which would give us 56 root 6. 56 root 6. 56 root 6. And add the 294 to the 16, we get 310. So our final answer would be 56 root 6 plus 310. So we've looked at multiplying monomials, then a monomial by a binomial and or a trinomial, and then finally multiplying binomials. We use a similar process as to how we would multiply in our polynomials with algebra. Very similar type of way that we would do this. So that concludes our lesson on the multiplication of radicals.